The specular light computation is based on blink phone shading model, and of course it has to take place at every pixel. Basically, we need to compute it in our fragment shader for every fragment that we generate. And the specular light intensity is based on the half vector. Half vector is computed as the incoming light vector right here, plus the inverted vector that points from the pixel position to the eye position. So it's the inversion of this vector. So L plus inverted E vector, which results in a vector like this. But of course we also have to point it in this direction, and this will give us our half vector, which is this vector right here. And blink phone shading model computes the intensity of the specular light as dot product between the normal vector and the half vector, and also raised to the power of shininess, which is basically just a factor of shininess is the value between 1 and 255. So this dot product right here is the dot product of these two vectors. So what matters is this angle between these two vectors, the normal vector and the half vector. And just like with diffuse light, what we do in practice is that we take the result of the dot product, and to just ignore any negative values which we cannot accept as our intensity, we just clamp it into the range from 0 to 1. The shininess of the specular light is computed as the dot product raised to the power of shininess, and it will vary per pixel as follows. So close to 1, you can see that this is just a large blind spot, but as the shininess goes up, we get closer to an impression of a smooth exterior reflecting the light and causing appearance of the specks like this on the object. And in practice, the shininess may range from 1 to somewhere close to 255. Our current Laboratory 7 project has both the diffuse and specular light computation done in the fragment shader. We already rotate our normal vectors, and we already pass the light position over to the fragment shader. And what's remaining here is to compute this eye vector right here. So that's what we need to be able to compute the specular light. And what we do is we take the original vertex position multiplied by the model matrix, which places it in the world space, then also multiplied by the view matrix, which transforms the vertex into the camera space. So now we have the camera space, and in the camera space our object is fully transformed like this with every vertex. And as we take the vertex in the camera space, the camera or position of the observer is located in the origin of the system of coordinates. Therefore, to get the eye vector, this vector, we simply take the vector that points to the vertex position in the camera space, like this. So this is my illustration, but this is really the vector that we compute here. E vector is the representation of this vector in our graphic. In the fragment shader, each of these inputs is normalized because interpolation may affect the lengths of vectors. And then we invert the direction of our E vector, which is this vector right here. So it needs to be pointing from the pixel position to the position of the camera. And then we compute the half vector by taking L plus E and normalizing that as well. So now we have our half vector. And here we apply our blink phone computation, taking the dot product of the normal and half vector, and then raising it to the power of shininess, which is passed on all the way as a uniform from our CPU program. This is giving us our intensity, and we simply take the specular color that we generate and pass on as a uniform, multiplied by this specular light intensity, and combine it with the rest of the color components that we want to assign to our final color of every fragment. In OpenGL, the sources of lights themselves are not visible automatically. If you'd like to model the source of light, you have to create an object and make it look illuminated just the way you like. And the two techniques that we could possibly use are the light computation done based on the vertex positions, which is kind of fast, and also the light per every fragment, which is slower, but makes the objects lit more realistically.